John, you're so excited about this class, you're attending twice. Obviously, Zoom is not behaving particularly stably. I will hope that it does better from here on in. So stars.chromeexperiments.com or something else crashed Zoom. So maybe check that particular program after class instead of during it. So you're observing two stars, star X and star Y. Star X has a parallaxic angle of 6 arcseconds. Star Y has a parallaxic angle of 2 arcseconds. Which one of these is true? I'm not going to ask you any mathy questions like this on a quiz or on a test, but this is there to think about. Go ahead and pause the video, think about it, draw a couple of pictures, and pick your answer. And the correct answer is A. Star X is 3 times closer than star Y. Now, I might ask you a question like this and have you have to determine which star is closer, but I won't include the math of you having to figure out how many times closer or further it would be. And then here's a discussion question. 6 hours later, which constellation will the sun be in and which constellation will be highest? 2 separate questions. Normally we go into discussion rooms to talk about this, and this is an important one. I will ask you both of these related questions at some point. So pause the video and really think about it before I give you the answer. So we're looking south. Which way is the sun which way is the sky turning, clockwise or counterclockwise? If you get confused by this, the way I always do, then my go-to way of remembering is that things rise in the east and set in the west. So hopefully everyone has paused and figured out what their answer is. The constellation that will be highest of the constellations shown is the constellation Cancer. But which constellation will the sun be in? And the answer is the sun will still be in the constellation Aries. The whole sky is turning at the same rate. The sun does move from being in one constellation to being in another because we're moving around the sun, but it takes about a month. So more math stuff that you don't have to worry about, but this is the technically correct definition. Brightness is the luminosity, how much light energy the star gives off per second, divided by 4 pi d squared, which is the area of a sphere. So that's the outer skin of a sphere. If you have a sphere of a certain radius d, and you need to cover that with wrapping paper, then you need 4 pi d squared worth of wrapping paper, if you don't waste any. So luminosity is measured in units of watts. This is the same unit that you see as power on your light bulbs and on some other electric devices. And as you might expect, the sun puts out a lot of watts. Again, this is why we use scientific notation. That's a ridiculous number to write out, but if you put it in scientific notation, it's manageable. I don't expect anybody to remember that figure. Just remember that the sun puts out a lot of energy. Once we know a star's distance, we can measure its luminosity by knowing how bright it is in the night sky. And typically, when we describe the luminosity of stars, we just describe the luminosity in terms of how much more luminous is it than the sun, or how much less luminous is it than the sun. Remember, the sun and the star's soul are the same thing. The name of our sun is technically Sol. So one could also say luminosity of Sol. So you're observing 2 stars. Star A is 10 times more luminous than the sun. Star B is 100 times less luminous than the sun. Star B is 200 times closer to Earth than star A. Which star appears brighter? So brightness depends on 2 things. It depends on how luminous it is, and it depends on how far away it is. But The far away has a power dependency of a square. It goes off as an area, and that's a stronger dependency than luminosity. So go ahead and pause, pick your answer. The correct answer is star B. Being much closer makes star B brighter in the night sky than star A. Even though star A is 10 times brighter than the sun, and star B is 100 times fainter than the sun. This is counterintuitive, but true. Now, I apologize for this, but I didn't do this, the ancient Greeks do, but the way that we measure brightness is backwards from the way that common sense suggests. The fainter something is in the night sky, the larger a number we associate with it. So our very best telescopes can see up to a brightness of magnitude 30. A 1 meter telescope, which is better than telescope you have in your backyard, can see up to a brightness of about magnitude 18. With binoculars, you can see things that have a brightness of about 9.5. Bernard's star, one of the closest stars to us, not visible with the naked eye. You would have to know precisely where it is and use binoculars in order to see it, because Bernard's star is that dim. Faintest object visible to the unaided eye is 6, and Alpha Centauri, one of the brightest stars in the night sky, is at 0. So the thing that gave us the apparent magnitude system is that there was some ancient Greek whose name I believe was Hipparchus, who just had pretty good eyes. And he just watched the night sky all the time. And one of his lifetime projects was that he categorized the stars by brightness. And to him, it looked like there were about 6 different levels of brightness of stars. And so he just labeled stars as having brightness 1, 2, 3, 4, 5, or 6, with 6 being the faintest and 1 being the very brightest. Because of how human eyes work, the difference between each of these levels of brightness is about 2.5. Something has to get brighter by about 2.5 times for your eye to detect that it is noticeably brighter than something else. And so he gave us a system, and we're stuck with it. Of course, there's things we can see that are even brighter than stars. So Venus at its very brightest has an apparent magnitude of -4-ish. The full moon is about -13. The sun is -22. So this is not how I would have created the system, but this is what Hipparchus made. And now we all have to live with it. So we discussed how distance and luminosity affects the brightness of stars. Now let's think about stars' color a little bit. Stars are blackbodies, which is a fancy word for an object that is emitting light and is not transparent to the light that it's emitting. So it's optically opaque, would be another way to put it. There's fancier ways to think about what a black body is, but that will serve us well enough. So coolish stars emit mainly red light. You get a little bit hotter and you're emitting mainly green light. And then you get super hot and you're emitting mainly ultraviolet light. And this tells you how we classify stars. Stars are designated by letters that denote how hot they are. O-type stars have an outer surface that's tremendously hot. F-type stars, a little bit hotter than our star. G-type star, which is what we are, has an outer surface that's between 5,000 and 6,000 Kelvin. And M-type stars have an outer surface in between 2,500 to 3,500 Kelvin, which is not much hotter than a light bulb. I want to emphasize that I'm talking about the outer surface of the star. The thing that powers all stars is nuclear fusion. And that happens when you get atoms to run into each other fast enough that they stick and release energy when they stick. Nuclear fusion requires millions of degrees Kelvin. So all these stars are real hot at their center. But their outer surface has a temperature that differs by quite a bit. And here they're all drawn the same size, but that's a bit of a lie. Their sizes are also quite a bit different. So there's the sun. The typical way to remember this is the mnemonic, oh, be a fine girl, guy, whatever, kiss me. I don't much like that one myself. I just have O, B, A, F, G, K, M memorized. But you're gonna wanna figure out some way of remembering it, because this is gonna be coming up for the rest of the class. Much of what we're gonna do from now on in is talking about how really little stars behave and how really huge stars behave and what the differences between that is. The super hot stars are far less common than the cooler stars. As a matter of fact, we can generalize that M-type stars are more common than K-type stars, or more common than G-type stars, or more common than F-type stars, so on and so forth. The vast majority of stars in the universe are M-type stars. So I've been showing you blackbody radiation curves. Let's look at a dynamic interaction of how these work. And I will hope that my laptop does not crash. Again. So that orange curve means how much power the star is jetting out at particular colors of light. So this star, which is pretty much the same as our sun, is emitting more power in blue-green than in any other color of light. Now it's emitting all the colors of light, visible light at least, but it's more greenish than anything else. Now let's adjust the temperature way down. This is more like the temperature that the very coolest stars are emitting. They're actually mainly emitting infrared light. They are emitting a little visible light, but mainly infrared. Makes them hard to detect. They also just aren't emitting that much light, period. And that makes them hard to detect too. The outer surface of an M-class star is not that much hotter than an old incandescent light bulb, which is about that temperature. A big part of the reason that we moved away from incandescent light bulbs is that the majority of the light they put out is in the infrared. I'm going to zoom in on the y-axis here so you can see it a bit better. And that's why people would say 90% of the energy from those old incandescent light bulbs is wasted, because 90% of the energy is going into colors of light that you can't see, wavelengths of light that your eyes can't interpret. It's not being wasted as heat. Those bulbs are still putting out a lot of energy, and they work perfectly well for keeping your fries warm, but they are not so good for illuminating things that humans want to look at. And then all the way down to the temperature of the Earth itself, as you've noticed, quite cool. Doesn't hurt to walk around on it. So I'm going to go back to sun level temperatures. And I'm going to compare the sun against a truly hot star, Sirius A, the dog star. So temperature's rising, 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 rising. And Sirius puts out so much power that it's now completely off the scale. So I'm going to change the scale on the y-axis again. Sirius is emitting primarily ultraviolet light. It's still emitting a lot of visible light, and far more visible light than the sun does. Compare Sirius to the sun. Sirius, the sun. So the truly hot stars are emitting a lot more power than the cooler stars. It's a dramatic difference. Back to the slides. So stars are not perfect black bodies. They don't actually just sit there with a sharp surface and only emit light. The cooler gas surrounding the star and the star's atmosphere absorbs some of that light. And so you see absorption lines right off the bat for almost every star from the starlight passing through the star's own atmosphere, which gives us a good sense of what stars' atmospheres are made out of. And surprise, surprise, it's usually hydrogen and a little bit of helium. But we do see more complicated and interesting things for some types of stars. And so here's the stellar spectrum from some anonymous G-type star. And those absorption lines are not due to some intervening body of cool gas. It's due to the star's own atmosphere. So we have absorption lines right from the get-go for most stars. And what you see absorbed depends highly on how hot the star is. So for the very hottest stars, we see helium that's had its electrons knocked off. The fancy word for that is ionized. Get a little cooler and you see helium that still is holding on to its electrons. You don't see hydrogen because the star's energy is so intense that it knocks the hydrogen way away from it right from the get-go. But as stars get cooler, you start to see hydrogen. Eventually, you start to see ionized metals. And to an astronomer, a metal means anything that isn't hydrogen or helium. So astronomers count carbon as a metal. And so you might see a little bit of carbon in the atmosphere, and an astronomer would say, oh, look, some metallic absorption lines, even though carbon isn't a metal. Again, this is just how astronomers do things. And to get even cooler than that, you start to see metals that are still holding on to their electrons. And so the very coolest stars are putting out so little energy that sometimes molecules are able to stably form in their atmosphere. And you start to see absorption lines from molecules. That means that not only are the elements holding on to their electrons, but they're able to find some other element that they're chemically compatible with and make a new compound, which only happens at pretty low temperatures. So I just want to remind you that looking at this information and knowing what elements are there is the main part of how we determine whether a star is moving towards us or away from us. Blue shifting and red shifting. Annie Jump Cannon, one of the many luminaries of astronomy, she classified thousands of stars by their spectra at Harvard University. And she's a person that invented this OBAFGKM system. So there's a very hot star, less hot, even less hot, and finally cool enough that it's not even emitting very much purple light. Annie Jump Cannon was working with an older system that went A, B, C, etc., but it wasn't based on temperature, but on gas composition. So she kept that system, but reorganized it to how hot the star's outer surface is. And that's why we're dealing with OBAFGKM and not something that would be more sensible and easier to remember. Astronomy is full of artifacts of the past like that. So measuring the shape, strength, and location of the absorption lines in the star spectrum tells us many things about the star. It tells us what the elements or even compounds in the star's atmosphere are, tells us how many of them there are, and the location tells us how fast the star is moving towards us or away from us. Each element leaves characteristic absorption lines. And if the star is redshifted or blue shifted, then those lines will be moved by a certain amount, and that corresponds mathematically to how fast the star is moving away from us or towards us. So there's magnesium, there's sodium, there's a little hydrogen. You can measure the chemical composition of the star's atmosphere. There's a strong line, that means there's a lot of it. A weak line, that means there isn't so much of it. A wide line can tell us about the rotation of the star, the gas pressure and temperature. So studying the sun's spectral lines and showing us exactly which atoms are present in the sun and how much of each atom there is. And the sun is almost entirely hydrogen and helium. Only trace amounts of oxygen, carbon, neon, nitrogen, so on and so forth. But even though there's only trace amounts, the sun still has a lot more oxygen than all the rest of the oxygen in the solar system put together. The sun still has a lot more carbon than all of the other carbon in the solar system put together. The sun is a dominant feature of the solar system. So if two identical objects are heated to different temperatures, which object gives off more total light? The hotter object, the cooler object, or do they give off the exact same amount of light? The hotter object. Hopefully you paused. And I am going to have to take a pause as well. Apparently I will be finishing this lecture in 3 different parts because I've just gotten an email that I'm needed for UC Berkeley work tasks. So there will be 3 videos at least that are uploaded. Sorry, I'll be back as soon as I can.